What happens when a wave travels forward and another wave travels backward at the same time? Surprisingly, the result may not look like a moving wave at all. Instead, a stationary pattern called a standing wave can form a phenomenon that plays a critical role in transmission lines, antennas, and RF system performance. In the previous lessons, we learned that electromagnetic waves can reflect when they encounter boundaries or impedance mismatches. This means that in many RF systems, both an incident wave and a reflected wave may exist simultaneously. At first glance, it might seem that these waves simply pass through each other and continue traveling independently. However, electromagnetic waves obey the principle of superposition, meaning that when multiple waves occupy the same space, their fields combine. This raises an important question. What happens when a forward-traveling wave and a reflected wave of the same frequency interact continuously along a transmission path? The answer leads to one of the most important concepts in RF engineering, the standing wave. A standing wave is a stationary wave pattern formed by the combination of two waves traveling in opposite directions with the same frequency. Unlike ordinary traveling waves, standing waves do not appear to move through space. Instead, specific locations experience maximum amplitude, while other locations experience minimum amplitude. These locations remain fixed rather than moving along the transmission path. The points of maximum amplitude are called antinodes, while the points of minimum amplitude are called nodes. The pattern remains stationary because the forward and reflected waves continuously reinforce and cancel each other at specific locations. Intuitively, imagine shaking one end of a rope while the opposite end reflects the wave back toward you. As the outgoing and incoming waves overlap, certain points on the rope move significantly, while other points barely move at all. The resulting pattern appears fixed in place. Physically, consider a transmission line connected to an improperly matched load. Part of the RF signal travels toward the load, while part reflects back toward the source. These two waves combine along the transmission line, creating regions of high voltage and low voltage. Mathematically, standing waves occur because the amplitudes of the forward and reflected waves add together according to the principle of superposition. Where the waves reinforce each other, maxima are created. Where they oppose each other, minima are formed. This produces the characteristic standing wave pattern. Standing waves are extremely important in RF engineering because they reveal how effectively power is transferred through a transmission line. Ideally, all transmitted power reaches the load, producing little or no reflection. When impedance mismatches occur, reflections increase and standing waves develop. Large standing waves indicate that a significant portion of the energy is being reflected rather than delivered to the intended destination. Engineers commonly measure standing wave behavior using VSWR, or voltage standing wave ratio. VSWR is one of the most widely used metrics in antenna systems, transmission lines, RF amplifiers, and microwave engineering because it provides a direct indication of impedance matching quality. Standing waves provide a visual and measurable indication of how electromagnetic energy behaves inside RF systems. They help engineers diagnose impedance mismatches, identify inefficient power transfer, and optimize system performance. A common misconception is that standing waves only occur in transmission lines. In reality, standing wave behavior can appear in antennas, resonant structures, waveguides, cavities, and many other electromagnetic systems whenever waves reflect and interact. Understanding standing waves naturally leads to another important concept. The relationship between electric and magnetic fields determines how energy moves through a medium. In the next lesson, we will explore wave impedance and discover how electromagnetic fields relate to one another during wave propagation. In this lesson, we learn that standing waves form when forward and reflected waves combine, creating stationary patterns of maxima and minima. We also saw how standing waves are directly related to impedance mismatches and why they are critical for analyzing transmission lines, antennas, and RF systems. In the next lesson, we will explore wave impedance and discover how electric and magnetic fields are related within an electromagnetic wave. If you found this useful, like the video, subscribe, and follow for the next lesson.